Hello students, welcome to the video lectures of speech and natural language processing. So today we are going to talk about the topic called smoothing. So let us try to understand what is smoothing, why smoothing is important, and types of smoothing that exist. And smoothing is a technique used to handle the problem of zero probabilities in language models. So especially in n-gram models. So why is smoothing necessary? It is because of data sparsity and generalization. So that means when we train an NLP, the model has to be very accurate such that it ensures that there won't be any kind of zero probability or the unseen words, I can say, that should not exist. So zero probabilities are, so there should not be any unseen words in the model what we are trying to train. Okay, let us say this is the NLP which you are trying to train with some database. So the database should not have any unseen words. So if there are any unseen words, what this smoothing ensures is it assigns some probability to it. Got it? So that is why smoothing is important. So types of smoothing. So first one is additive smoothing. So also called Laplace smoothing. So this is one of the simplest smoothing technique where a small constant that is typically 1 is added to all the observed n-gram counts to ensure that there is no n-gram has a probability of 0. So additive smoothing prevents zero probabilities by assuming every possible n-gram has been observed at least once, even if it has not appeared in the training data. So the formula is this. So this is the formula, and count of words is the number of times the word W appears in the dataset. N is the total number of word occurrences in the dataset. V is the vocabulary size. Alpha is the smoothing parameter. Typically, we have a small positive number like 1 or less than 1 is taken into the account, right? So what it does basically is, so for example, if you consider any database, I'll just tell you. Let us say we have a database which we are sending it for training. So let me write some words and number of counts that is repeated. So let's say I have a word called cat, which is repeated 3 times. And if I have a word called dog, which is repeated 2 times. And if I have a word called mouse, which is having 0 as its count, which means this is something an unseen data, we can say. So now the value of n would be 5. That is, what is n? N is the total number of word occurrences in the dataset. So there are 3 cats, 2 dogs, and 0 mouse. So add these 3 things, what you will get? So total is 5. That is what our n is. Next, we have V, that is size of the vocabulary. So how many kinds of unique words that exist in the database? So mouse is 1, dog is 1, cat is 1, right? So there are total 3. So now basically what this additive smoothing does is, so now let's write the normal probabilities of each word that is mentioned here. So probability of cat appearing would be, so 3 by 5. 3 is the number of times the cat word has the count, and we divide it with n. So what is n? N is the total number of word occurrences in the data set. So the probability is 0.6. Similarly, the probability of dog would be what? So it is 2 by 5. That is 0.4. Similarly, what would be the probability of mouse? So that is 0 by 5, which is 0. Now, if you apply this, after applying the additive smoothing, so what happens is additive smoothing. So now the probabilities will become in this way. Probability of cat would be, so just substitute it in a formula, where please consider alpha as 1. So this one. Consider alpha value as 1. That is our Laplace smoothing technique. What it becomes is, now I'm calculating the probability of cat, which is repeated or having count as 3. So 3 plus 1 by 5 plus 1 into 3, which equals 4 by 8. That is 0.5. Similarly, if you calculate for the probability of dog, the probability would be 0.375. And the probability of mouse, which is the core thing what we are trying to talk, or the important one is mouse, where since we added 1 to it, it becomes 1 by 8. The probability is 0.125. So this is the probability of the word mouse. Earlier, the probability of mouse was 0. That is when we didn't apply the additive smoothing. But when we applied additive smoothing, it became 0.125. So this is how it tries to ensure that no zero probability exists. Similarly, we have another couple of smoothing algorithms. So next one is Good-Turing smoothing is another algorithm which we have. And it also, so it adjusts the probability estimates by redistributing the probability mass of low frequency n-grams to unseen n-grams. Got it. So what basically it does is it just redistributes some of the probability mass from the observed events. It is just to handle the likelihood of these unseen events only, such that the model what we are trying to make will be more robust. Clear, students? Then it is Kneser-Ney smoothing. So that is, this is a smoothing technique, and it's an advanced smoothing technique that not only adjusts the probabilities for unseen n-gram, but also takes into account how likely a word is to appear in new contexts. Okay. That is the specialty of Kneser-Ney smoothing. Here we have two terminologies to discuss. That is, one is continuation probability, other is discounting. So continuation probability, what it makes is it just try to estimate the probability of the word occurring as a part of a new combination. And discounting is nothing but this will try to reduce the probability assigned to frequent n-grams and just redistributes this discounted probability mass to the less frequent unseen n-grams. Then we have absolute discounting. So where this technique subtracts a fixed discount from each non-zero count and distributes the total discounted probability mass to unseen n-grams. Clear, students? So here also what happens is similarly what I told to you earlier in the additive smoothing. Here also it will have some corpora database, and let's just divide this into some other n-grams. Let us take a bigram. So here we'll write the count of those, that is bigrams. So in the sense, let me take one database like this, a bigram one, and then the count. So let us say I have couple of database, the cat. So this is repeated for 4 times, let us say, and I have the sat repeated for 1 time, cat sat. Let us say this is repeated 2 times, and sat the, this is 0. So just I have a center, this is not repeated. So now, so typically here only thing what we have to assume is just we need to assume the D value. What is D? D is the discount value. Let's say it is 0.75. Just let us assume. So then you will come to know how this formula is working and how this discounted value is being used. So now, for example, the count of the context of the C of D, let us take, is 5, right? So that is the total number of D that is followed by any word in the dataset is 5 times. Let us imagine. And so now the total number of bigrams that exist are 7, right? In the database, there are 4 plus 1 plus 2 plus 0. That is 7. So I'm writing here the total number of bigrams as 7. So the observed n-gram, sorry, the observed bigrams now we'll try to understand. So observed bigrams of, let us say, cat and the. So the just we substitute this in our formula. So count of the comma cat by count of the, and just we have to minus or subtract this discount value. Is 4 minus 0.75 by 5, which becomes 0.65. Right? Now, the unseen bigram, that is probability of the sat. Right? This is the unseen bigram, what it is mentioned, right? So now we just put it into the formula n1 d by n. That is, it becomes 2 by 7. Because now what I'm trying to tell you is, let us imagine this value of n1 is equal to 2, which means the appears in 2 unique bigrams, right? This D is appearing in 2 unique bigrams. That is, the cat is 1, the sat is another. Now, if we substitute these things in the formula, what we get? That is 2 by 7, which means approximately equal to 0.2857. Right? So the example, what we considered is just to explain you that, the absolute discounting will try to redistribute the probability mass just by lowering the probabilities of observed events. Then we have Backoff models. So in Backoff models, if the n-gram probability is not available, example, because it's an unseen n-gram, the model backs off to a lower order model from trigram to bigram or bigram to unigram. So this is the formula for a Backoff algorithm model, where alpha is the Backoff weight, where Backoff models are useful for handling data sparsity by recursively reducing the context size until a reliable estimate can be found. So what does this Backoff algorithms does basically is, so if you consider a corpora or the database, which is similar to the earlier examples, I'll just explain you with So you can see here, this is count of, I'll just write down here since that is very small. Count of Wn minus 2, Wn minus 1, and Wn. So this is the count for what? Trigrams, right? Trigrams are these, all right, which is mentioned here. Then count of n minus 2 and n minus 1 is the context or is the count of our bigram context. Sorry, that is n minus 2 comma n minus 1. And of course, alpha is the Backoff weight, which is already given. And probability of this Backoff algorithm would be word n into word n minus 1 is the Backoff probability using the bigram. So just we assume there will be one database again where we take some trigrams and bigrams as a part of our database, and we also write down the counts of the trigram and bigram which have mentioned, and just we try to assume the Backoff weight, and we just substitute the things in the formula. So after applying, what it ensures is whichever the trigram that is unseen in the dataset or any other bigram or trigram that is unseen in the dataset, it will just allow us to calculate a smooth probability just by backing off it to some other word. That is, if you have unseen a word called cat sat on, let us imagine there is a word cat sat on. So this is a trigram, right? This is a trigram. And this trigram is unseen in the dataset. So this is an unseen word, unseen trigram which is existing in the database. So now what does this cat's Backoff does is it just allows us to calculate a smooth probability by backing off to a bigram. From trigram to it backs off to bigram. Then advantages of smoothing. First one is it prevents zero probabilities, yes, and it improves the generalization, handles sparse data. So limitations are overestimation of rare events and computational complexity. So these are the various advantages and the limitation that exists with the smoothing technique. So when I say overestimation, so this is the overestimation of some rare events. That is, so suppose we have suppose there are some probability of our rare or unseen engrams are present, which will lead to the loss of our accuracy, right? And since the computational complexity also same, suppose some there are some advanced smoothing techniques which just we have seen like Kneser-Ney or some Good-Turing, which are computationally very expensive, and this imposes a challenge to implement on a large scale of data since we have cost occurring more, right? So that's it. Thank you, students.